The Merlin engine's final splutter told Flying Officer Michael Appleby all he needed to understand. His Spitfire wouldn't reach Biggin Hill. Coolant poured from the radiator, white vapor marking his desperate path as he guided the wounded fighter toward Hawkinge, the forward base positioned on the cliffs near Folkestone. October 17th, 1940. The Kent skies had attempted to end his life for the third time that week. The Messerschmitt Bf 109 that had ambushed him from above did far more than spray his plane with 7.92mm bullets. A cannon round from the second attack had ripped through the rear fuselage like opening a can, creating a hole big enough for 2 fists. When Appleby finally nursed the Spitfire onto Hawkinge's grass runway, the aircraft settled with a disturbing groan. Ground crew raced toward the fighter before the propeller finished spinning, their expressions changing as they saw the destruction. Sergeant Fitter James, Jimmy McCudden, nephew of the Great War ace, though he'd never pilot an aircraft himself, walked around the damaged machine wearing the grim look of a doctor examining a critical patient. The cannon hit had torn through 3 stringers and destroyed the fabric-covered section behind the fuselage frames. Even worse, it had fractured the aluminum longerons, those load-bearing spine members preventing the tail from collapsing under G-forces. Standard procedure dictated one outcome: salvage the aircraft for components and give Appleby a replacement from the shrinking reserve pool. But October 1940 permitted no such extravagance. Fighter Command had lost 1,023 aircraft since July. Supermarines assembly lines were producing roughly 320 Spitfires each month, but combat losses, training crashes, and factory bombing raids meant squadrons operated at 60% strength on fortunate days. Every salvageable airframe counted, even those appearing beyond rescue. McCudden knelt beside the torn fuselage, running his fingers across the jagged metal. The aluminum alloy, Alclad 24ST, a copper-aluminum mixture created specifically for stressed skin aircraft, had bent but hadn't shattered entirely. The fabric covering the rear fuselage frames, originally sewn there for weight savings where complete metal skinning wasn't structurally necessary, hung in shreds. He checked his watch. 16:47 hours. Dawn Patrol would launch at 05:30 tomorrow, and 92 Squadron needed every fighter available. The Luftwaffe had struck London with 350 bombers the night before, and intelligence indicated another massive raid was forming. Right then, McCudden said to his team of 6 fitters and riggers surrounding the wounded Spitfire, "We're not scrapping her. Open the fabric stores and locate the Irish linen rolls, the heavy grade, not the training material. Someone wake Corporal Davies in the dope shop. Tell him we need 5 gallons of clear cellulose, 2 of red. And if he grumbles about requisition paperwork, remind him the Germans don't file forms before dropping bombs." The choice to attempt a fabric and adhesive repair on a combat aircraft might appear like desperation masquerading as cleverness, but it relied on solid aeronautical engineering fundamentals dating back to military aviation's origins. The Spitfire, for all its modern, stressed skin construction, forward of the cockpit, retained fabric-covered control surfaces and rear fuselage sections as a deliberate design decision. Reginald Mitchell's original calculations had established that fabric covering over tubular frames provided sufficient strength at a fraction of the weight for areas experiencing lower aerodynamic pressures. What made this repair unconventional wasn't using fabric. It was applying traditional methods to battle damage that had compromised the metal structure underneath. McCudden's gamble depended on a hybrid strategy, reinforcing the fractured aluminum longerons with splintered metal strips, then covering the entire damaged area with multiple linen layers and cellulose dope to restore both the aerodynamic surface and provide additional structural support. The repair needed to withstand not merely straight and level flight, but the savage punishment of combat maneuvering. 6G turns that quadrupled the aircraft's effective weight, dive speeds approaching 450 miles per hour, and vibration from Browning machine guns firing well over 200 rounds per minute, just inches from the repair location. As the ground crew started hauling equipment from the maintenance tents, McCudden outlined the repair plan in his logbook by flashlight. The October evening was approaching quickly, and the forecast promised clear weather, ideal for Luftwaffe bombers, terrible for anyone attempting to work undetected on an exposed airfield. Hawkinge sat directly beneath the Luftwaffe's approach paths to London. The crew would be handling flammable cellulose dope and acetone, whilst German formations flew overhead. One incendiary bomb in the wrong spot would transform the repair operation into an inferno. But that was the arithmetic of survival in October 1940. You worked through the terror, because the alternative meant one fewer fighter in tomorrow's battle. And tomorrow's battle was where the war would be won or lost. The fabric rolls McCudden's team retrieved from the maintenance stores weren't some improvised replacement. They represented decades of refined aeronautical engineering. Grade A Irish linen, woven from flax fibers to an exact specification of 4.5 ounces per square yard, had covered military aircraft since before the Great War. The material arrived in 36-inch wide rolls, its natural tan color soon to be transformed by the chemical process that would make it rigid, waterproof, and capable of bearing aerodynamic pressures. Each yard cost the Air Ministry 2 shillings and sixpence, though by October 1940, procurement officers weren't arguing about costs. The linen itself was merely the foundation. What truly made fabric covering function was the dope, a term that sounds crude until you grasp the chemistry involved. Cellulose acetate dope consisted of cellulose nitrate dissolved in a volatile solvent mixture of acetone, amyl acetate, and butyl alcohol. When brushed onto fabric, the solvents evaporated quickly, leaving behind a clear, flexible film that penetrated the linen's weave and bonded the fibers into a unified membrane. Multiple coats built up a skin that was simultaneously airtight, weatherproof, and remarkably strong under tension. The chemical formulation used by the RAF in 1940 traced its origins to compounds developed by the Kellon Company in 1913, refined through millions of flying hours on everything from SE-5As to Hawker Hurricanes. Corporal Arthur Davies arrived at the Spitfire with his dope kit at 17:20 hours, his coveralls already stained with the telltale purple-red of pigmented coats. The smell hit you immediately, a sharp, sweet chemical reek that burned the nostrils and lingered in your throat. Extended exposure caused headaches and nausea, which explained why dope shops were positioned downwind of main maintenance areas and equipped with ventilation fans that seldom worked properly. Davies had been applying dope since 1936 and could judge viscosity by sound alone, listening to how the liquid poured from its container. "You're having a laugh, Sarge," Davies said, surveying the damaged fuselage. "This isn't patching a torn aileron. You want me to dope over fractured alloy? The expansion rates don't match. Fabric contracts as it cures. Metal doesn't give. You'll get wrinkles at best, delamination at worst." McCudden had anticipated this objection. "We're not depending on adhesion alone. The fabric goes over splintered reinforcements, and we're stitching every 6 inches to the frame members. The dope seals it, but the mechanical fastening carries the primary loads. I need you to mix the batches thin for the first 3 coats. We want penetration into the weave, not surface buildup. Then standard viscosity for coats 4 and 5. The repair plan required materials that existed in different sections of the store's system, each with its own logistical complications. Anti-aircraft thread, a waxed linen cord specifically manufactured for rib-stitching fabric to airframe members, came in 1-pound spools and had to be requisitioned from the riggers' stores. The stitching needles were curved, surgical-grade steel, 3 inches long, with triangular points designed to pierce fabric, and wooden ribs without splitting the grain. Aluminum patch plates, normally used for minor skin repairs, would need to be cut and drilled to splint the fractured longerons, and the repair demanded tensioning, which meant controlled heat application using a domestic iron borrowed from the station commander's quarters, because proper fabric tensioning irons had been requisitioned by Coastal Command 3 months earlier. The science behind dope's effectiveness resided in its tensile properties once cured. A 5-coat dope finish on grade A linen achieved tensile strength approaching 80 pounds per square inch, not remotely comparable to aluminum alloy's 27,000 psi yield strength, but more than adequate for covering non-primary structure. What made doped fabric particularly suitable for aircraft repairs was its behavior under stress. Unlike metal, which fails catastrophically when cracks propagate, fabric stretches slightly under load and distributes stress across its entire surface area. A properly applied fabric skin acts like a drumhead, maintaining shape through tension rather than rigidity. McCudden's team also needed anti-tear tape, narrow strips of linen fabric pre-treated with dope, used to reinforce edges and prevent rips from propagating. Surface tape would cover every rib stitch line, creating smooth aerodynamic contours and preventing the stitching itself from creating turbulent air pockets. Then came the pigmented dope, aluminum powder-loaded coats for the base layers, providing both UV protection and the distinctive silver finish, followed by the roundel colors and identification codes that would need repainting after the repair. The chemical interaction between dope coats was equally critical. Apply a fresh coat before the previous layer had fully cured, and the solvents would redissolve the underlying film, creating a chemically bonded laminate. Wait too long, and subsequent coats merely sat atop the cured surface, vulnerable to delamination. The timing window was roughly 45 minutes in October temperatures, longer in winter cold, shorter in summer heat. Davies would need to maintain a relentless coating schedule through the night, which meant working by flashlight while hoping the Luftwaffe stayed focused on London rather than strafing coastal airfields. The toolkit also included less obvious items. Talcum powder prevented fabric from adhering to itself during handling. Methylated spirits cleaned tools between dope applications. Razor blades trimmed excess fabric with surgical precision. Chalk marked rib positions on the linen before cutting. And somewhere in the supplies sat the Air Ministry's official instruction manual, AM 1925, Fabric Covering of Aircraft. A 47-page technical document that McCudden had long since memorized, but kept handy for settling disputes about proper procedure. As the crew assembled their materials beneath the Spitfire's wing, the enormity of the task settled over them like the approaching darkness. They were about to rebuild a section of fuselage using techniques borrowed from 1917 on an aircraft designed to fight at speeds those Great War pilots would have considered suicidal. And they had roughly 36 hours before someone would need to stake their life on the soundness of their work. The first Heinkels formations passed overhead at 21:45 hours, their unsynchronized engines creating the distinctive throbbing drone that had become the soundtrack to Britain's autumn nights. McCudden didn't look up. His hands were elbow-deep in the Spitfire's fuselage, probing the extent of internal damage by flashlight, whilst his rigger, LAC Peter Thornhill, held a second torch at an angle to eliminate shadows. The searchlights, stabbing upward from Dover, cast wandering illumination across Hawkinge's dispersal area, and every few minutes the distant thump of anti-aircraft guns reminded them that their work was occurring inside an active war zone. The repair timeline McCudden had sketched allowed no margin for error. His methodology was brutal in its simplicity. Strip damaged components by midnight, complete structural reinforcement by 0400 hours, apply fabric covering from 0500 through 1400 hours on October 18th, final dope coats, and curing through the night of the 18th and 19th, ground engine run at 0600 on October 19th. If everything went perfectly, and nothing in wartime maintenance went perfectly, they might have the Spitfire ready for air test by mid-morning on the 19th, giving the squadron one additional fighter for afternoon operations. The clock became their adversary immediately. Removing the torn fabric and damaged stringers took until 0120 hours, 3 times longer than estimated. The cannon shell had done more than tear. It had deformed the aluminum structure in ways that weren't visible until they started dismantling. 2 fuselage frames had buckled slightly, requiring careful cold working with leather mallets to restore their geometry. 1 stringer had fractured completely through, necessitating fabrication of a replacement from stock aluminum angle, and the main longeron crack extended 4 inches further than initially assessed, running dangerously close to a bulkhead attachment point. Thornhill, a former sheet metal worker from Birmingham who traded factory wages for RAF pay, took charge of the metalwork repairs. He cut reinforcement strips from 20-gauge aluminum sheet, drilling rivet holes with a hand drill because the pneumatic tools were too loud for night operations. Sound carried across the channel, and Hawkinge's defenders preferred not to advertise active maintenance that might attract Luftwaffe attention. Each rivet required precise buck-and-shoot technique, one man holding the bucking bar against the rivet's interior end, whilst another drove it home with a pneumatic gun operating at minimal pressure to reduce noise. 37 rivets went into the longeron repair alone, each one taking roughly 3 minutes to properly set. The fabric preparation happened simultaneously in a blacked-out maintenance tent 50 yards away. LAC Margaret Hendry, one of the Women's Auxiliary Air Force members attached to Hawkinge's ground crew, measured and cut linen panels using patterns McCudden had chalked onto the tent floor. Pre-war regulations had restricted WAAF personnel to administrative and support roles, but by October 1940, such niceties had evaporated. Hendry had learned fabric work on tiger moth trainers and understood the critical difference between cutting on the bias versus straight grain. Fabric cut parallel to the weave threads possessed maximum strength, whilst bias cuts allowed the material to conform to compound curves. She cut 4 primary panels, 2 lateral sections for the fuselage sides, 1 dorsal panel for the top surface, and 1 ventral piece for the underside. Each panel included 3 inches of overlap beyond the actual repair area, because joining fabric mid-span created weak points. The panels would overlap at the longeron positions, with rib stitching providing mechanical attachment at 6-inch intervals. Hendry also pre-cut 32 inches of anti-tear tape for every rib stitch line, plus reinforcement patches for the 4 corners where stress concentration was highest. By 03:15 hours, McCudden's metal repairs were complete but untested. There was no way to stress test the reinforced structure without installing it in an aircraft and flying it, which was precisely what they intended to do. The splintered longeron looked agricultural compared to the original monocoque construction, but the engineering was sound. Aluminum's yield strength meant the repair would either hold completely or fail catastrophically. There was no middle ground. The rivet pattern distributed loads across 12 square inches of structure instead of concentrating stress at the crack point, and McCudden had deliberately oversized the reinforcement plates to provide additional safety margin. The fabric installation began as dawn's first grey light crept across the channel at 05:20 hours. This was the critical phase requiring coordination between 4 crew members working in carefully choreographed sequence. Thornhill and LAC Dennis Cooper stretched the first lateral panel across the fuselage's port side, pulling the linen taut but not excessively tight, Overtensioning before doping caused the fabric to split when chemical shrinkage added additional stress. McCudden followed behind them with curved needle and waxed thread, rib-stitching the fabric to the fuselage frames using the modified Sen knot specified in AM 1925. Each stitch penetrated the fabric, wrapped around the frame member, and locked back through itself to create a mechanically redundant attachment that wouldn't unravel if one stitch failed. Hendry applied the first dope coat at 0635 hours, working methodically from one end of the panel to the other with a 4-inch brush. The clear cellulose went on thin and runny, soaking into the linen's weave and filling the microscopic gaps between fibers. The chemical smell intensified immediately, sharp enough to water the eyes. Within minutes, the fabric's color darkened as dope penetrated, and the material began to stiffen. The first coat wasn't about strength, it was about bonding the fibers into a unified membrane that subsequent coats would reinforce. At 0720 hours, the air raid sirens wailed. A German reconnaissance Dornier had been spotted over Dungeness, probably photographing bomb damage from the previous night's raids. Standing orders required all ground personnel to take cover during alerts. But McCudden made a battlefield calculation. The fabric couldn't be left partially doped and exposed to morning dew. "Keep working," he ordered quietly. "If you hear cannon fire, then worry about shelters." The Dornier never came close, but the interruption cost them 20 minutes of lost nerve before hands steadied and the rhythm resumed. By 0900 hours, 3 coats covered the port panel, and they'd begun stretching the starboard fabric. By 1200 hours, both lateral panels and the dorsal section were installed and carrying 4 coats each. The ventral panel, the most awkward to access with the aircraft sitting on its undercarriage, went on during the afternoon, requiring 2 crew members to lie on their backs beneath the fuselage whilst feeding fabric into position. Through it all, the clock consumed their safety margin. Each delay compounded, each unexpected complication chewed away minutes they didn't have. And hanging over everything was the knowledge that this repair's ultimate test wouldn't happen in a maintenance hangar. It would happen at 15,000 feet with a pilot's life, depending on whether adhesive and fabric could withstand what cannon shells and stressed aluminum barely survived. The rib-stitching technique McCudden employed wasn't some improvised field expedient. It was a precisely defined procedure that demanded both strength and craftsmanship. Each stitch began on the fabric's exterior surface, penetrated through the linen, wrapped around the underlying fuselage frame, then locked back through the fabric 4 millimeters from the entry point. The waxed thread, pulled tight with practiced tension, created a mechanical bond that didn't rely on adhesive properties. McCudden's hands moved in automatic rhythm, muscle memory from 3 years of fabric work, guiding the curved needle through its figure-8 pattern. 6 stitches per frame member, 8 frame members across the repair area, 4 separate fabric panels, 192 individual stitches before the job was complete. The spacing mattered enormously. Place stitches too far apart, and the fabric could balloon between attachment points under aerodynamic pressure, creating drag-inducing wrinkles, or worse, tearing loose entirely. Position them too close together, and you'd perforate the fabric to the point of weakness, creating a line of perforations like a postage stamp ready to tear free. The Air Ministry specification called for stitches at 6-inch intervals on primary structure, 8 inches on secondary areas. McCudden split the difference at 7 inches across the repair zone, conservative enough for safety, spaced enough to avoid over-weakening the linen. Once the mechanical attachment was complete, Corporal Davies began the critical doping sequence. The first coat had already penetrated and partially cured, stiffening the fabric but leaving it still slightly porous. The second coat, applied at 0745 hours, went on with precisely the same thin viscosity. Davies worked with steady brush strokes, overlapping each pass by 1/2 inch to ensure uniform coverage. No holidays, the doping term for missed spots, were acceptable. Any gap in the coating would allow moisture penetration, and moisture was fabric's mortal enemy, rotting the linen fibers and delaminating the dope film. The waiting period between coats was excruciating. Apply too soon, and the solvents from the fresh coat would redissolve the underlying layer completely, turning the careful buildup into a puddled mess. Wait too long, and the chemical bonding window closed, meaning subsequent layers merely sat atop the cured surface rather than integrating into a unified laminate. Davies judged cure time by touch, pressing his fingertip lightly against an inconspicuous section of fabric. When the surface felt dry but still yielded slightly to pressure, what old-timers called tacky dry, the next coat could go on. In October's cool temperatures with moderate humidity, that window arrived roughly every 55 minutes. The third coat went on at 09:25 hours, and here the technique shifted. Davies had mixed this batch to standard viscosity rather than the thinned formula used for initial coats. This layer began building surface thickness rather than merely penetrating. The brush strokes remained visible in the wet dope, creating a slightly textured surface that would disappear under subsequent coats. Watching dope cure was like observing a minor miracle of chemistry, the glossy wet surface gradually dulling to satin, then to a taut drum-like finish as the solvents evaporated and the cellulose film contracted. But contraction created a problem McCudden had anticipated. As each dope coat cured and shrank, it pulled the fabric tighter across the fuselage frames, increasing tension dramatically. This was desirable to a point. Taut fabric provided a smooth aerodynamic surface and resisted flutter at high speeds. Excessive tension, however, could literally pull stitches through the linen, or worse, deform the underlying aluminum structure they'd just repaired. The solution involved careful monitoring and, if necessary, controlled heat application to accelerate curing and manage tension buildup. LAC Hendry appeared at 10:35 hours with the station commander's iron, its chrome surface scratched from non-aviation use, but its heating element still functional. McCudden had her test the temperature on scrap fabric first. Too hot, and the dope would blister and discolor. Too cool, and the tensioning effect wouldn't engage properly. The correct temperature felt uncomfortable when held 6 inches from your cheek, but didn't quite burn. Hendry played the iron's face across the doped fabric in smooth, continuous strokes, never lingering in one spot. The fabric responded immediately, contracting further and producing a resonant tone when tapped with a knuckle. The surface transformed from slightly wavy to glass smooth, stretched tight as a snare drum head. The fourth coat, applied at 12:15 hours, incorporated aluminum powder pigment for the first time. The silvery paste went on thick and opaque, obscuring the linen texture beneath and beginning to establish the Spitfire's characteristic appearance. This coat served multiple purposes. UV protection, since raw cellulose degraded rapidly under sunlight exposure, thermal reflection to prevent heat buildup in the fabric, and the foundation for subsequent camouflage. Davies worked more slowly now, because pigmented dope showed every brush stroke and overlap line. Achieving a smooth finish required steady pressure and overlapping strokes at consistent angles. Between the fourth and fifth coats, surface tape went on. Narrow strips of pre-doped linen that covered every rib stitch line. Thornhill positioned the tape carefully, pressing it into still tacky dope so it bonded chemically, while also bridging the slight depressions where stitches penetrated the fabric. The tape created continuous, streamlined contours, eliminating the tiny turbulent pockets that would otherwise form around each stitch point. 48 linear feet of surface tape went onto the repair, each strip smoothed meticulously to avoid wrinkles or bubbles. The fifth and final clear coat went on at 17:20 hours on October 18th, nearly 24 hours into the repair sequence. This coat served as the sealant and protective layer, filling any remaining surface imperfections and providing a glossy finish that shed water and resisted abrasion. Davies applied it generously, allowing the dope to self-level into a uniform thickness. As the brush passed over the surface, the wet film caught the late afternoon light, showing rainbow interference patterns, a sign that the coating thickness was approaching optimal depth. Now came the hardest part, waiting for the repair to cure fully. Dope achieved handling strength within hours, but full structural cure required 18 to 24 hours depending on temperature and humidity. Touch the surface too soon, and you'd leave fingerprints in the finish that could never be polished out. Stress the repair prematurely, and you risked delamination between coats. McCudden posted L.A.C. Cooper as a guard to ensure no well-meaning personnel disturbed the Spitfire overnight. As darkness fell on October 18th, the repaired fuselage gleamed dully in the dispersal area's shielded work lights. It looked nothing like factory-fresh construction. The fabric panel edges were visible as slight ridges. The aluminum pigment didn't quite match the factory paint. And if you knew where to look, you could see the ghost outline of the reinforcement structure beneath. But it was whole. It was sealed. And come morning, it would either fly or it wouldn't. There was no in-between. Flight Lieutenant Jeffrey Wellum arrived at Hawkinge's dispersal at 06:15 hours on October 19th, his face showing the particular exhaustion that came from sleeping in full flying kit. He'd been posted to 92 Squadron 3 months earlier, fresh from operational training, and had already logged 47 combat sorties. At 19 years old, he was among the youngest Spitfire pilots in Fighter Command, though you wouldn't know it from the grey pallor that lack of sleep had etched into his features. McCudden intercepted him halfway to the crew room with a mug of tea and an uncomfortable conversation. "Your kite from the 17th is ready for air test, sir. She's had major repairs to the rear fuselage, fabric and dope over structural reinforcement. Ground crew are confident, but you'll want to take her up gently for the first flight." Wellum took the tea and studied the Spitfire sitting on the hard standing. Even from 50 yards, the repair was obvious. The fabric section broke the otherwise seamless metal contours, and the color match was off by several shades. "Define gently, Sergeant. Jerry won't come at me gently if this repair decides to part company at 15,000 feet. Standard air test procedure, sir. Climb to 8,000 feet over the field. Run through your handling checks at reduced power settings. Work up to combat speeds gradually. If she feels wrong, any vibration, any unusual control forces, you bring her straight back down. We've got a replacement aircraft on standby if this one won't pass muster." But both men knew the replacement didn't exist. The squadron's operational strength that morning stood at 11 serviceable Spitfires against an establishment of 19. Every fighter mattered, even ones held together with Irish linen and hope. Wellum completed his external inspection at 06:35 hours, running his hands along the fabric repair with the careful attention pilots develop when their lives depend on ground crew competence. The doped surface felt rigid under his palms, drum-tight and smooth. The rib stitching was precise, the surface tape perfectly aligned. Whatever else you could say about Hawkinge's maintenance section, they didn't produce shoddy work. He checked the control surfaces. Elevators responsive, rudder movement free and correct, ailerons smooth through their full travel. The pre-flight ritual was identical to every other sortie, yet everything felt weighted with additional significance. The Merlin fired on the third blade, settling into its characteristic burbling idle. Wellum let it warm for 5 minutes, watching the coolant temperature creep upward whilst scanning the instruments for any anomaly. Oil pressure 60 pounds per square inch. Fuel pressure 3 psi. Magneto checks normal. Everything precisely as it should be, which somehow made the apprehension worse. Known problems announce themselves. It's the unexpected failures that kill you. He released the brakes at 0647 hours and taxied to Hawkinge's eastern threshold, the grass strip still wet with morning dew. The windsock hung limp, dead calm conditions, which meant any handling peculiarities would be purely the aircraft's fault, rather than atmospheric turbulence. Wellum ran through his takeoff checks mechanically. Trim neutral, flaps up, mixture rich, propeller pitch fully fine, radiator shutter open. His left hand eased the throttle forward, whilst his right held the control column steady against the Spitfire's tendency to swing right as the Merlin developed power. The acceleration pressed him back into the seat. That familiar sensation of a Merlin's 1,300 horsepower converting fuel into forward motion. 50 miles per hour, 60, 70. The tail lifted and the Spitfire's nose dropped to the horizon. At 85 miles per hour, Wellum eased back on the stick and the fighter unstuck from the grass, climbing away at 160 indicated. Undercarriage up, throttle back to climbing power, settle into the ascent. So far, perfectly normal. At 2,000 feet, he began paying attention to what the airframe was telling him. Aircraft communicate through vibration, through the pressure on control surfaces, through subtle sounds that experienced pilots learn to interpret. He'd expected something, a buzz from the fabric section perhaps, or unusual flexibility in pitch control. Instead, the Spitfire felt entirely ordinary. The fabric repair neither drummed nor whistled. The handling was crisp and responsive. If anything felt different, it was the slight reduction in all-up weight from the fabric covering being lighter than equivalent aluminum structure would have been. At 5,000 feet, Wellum attempted his first proper maneuver, a gentle 30-degree banked turn to port. The Spitfire responded instantly, rolling smoothly into the turn with no adverse yaw or unusual control forces. He reversed the turn to starboard, testing the other direction. Again, completely normal. He pulled into a moderate climb, loading the airframe to approximately 2 Gs, feeling for any tendency of the repair to distort or separate. The fabric section behaved exactly like the metal structure surrounding it, transmitting no vibration or flexing through the control column. At 8,000 feet, he leveled off and conducted the prescribed handling tests. Stall approach with undercarriage and flaps down. The Spitfire shuddered at 73 miles per hour and dropped its port wing gently, exactly as designed. Recovery immediate and clean. Accelerate to 250 indicated and attempt a 4G turn. The aircraft pivoted around its center of gravity with no complaints, the fabric repair silent and solid. Reduce power and extend dive brakes. No vibration, no buffet, no indication that anything was remotely unusual about this particular Spitfire. The acid test came last. A power dive to maximum speed. Wellum rolled inverted, pulled the nose down through the vertical, and let the Merlin's power and gravity accelerate the fighter downward. The airspeed indicator wound rapidly clockwise, 280 miles per hour, 320, 350. The wind noise rose to a shriek as the Spitfire plummeted through 6,000 feet. At 380, indicated, well into the yellow warning arc, Wellum eased back on the stick, pulling out of the dive in a smooth 4G arc that compressed him into his seat and grayed his vision at the edges. The fabric held. No vibration, no deformation, no catastrophic failure. The repair had survived stresses that would have tested factory-fresh structure. Wellum keyed his radio transmitter. Scaffold. Bellboy read 2. Air test complete. No defects noted. Request permission to rejoin circuit. He landed at 0734 hours, the Spitfire touching down on Hawkinge's grass with barely a chirp from the tires. McCudden was waiting as Wellum climbed from the cockpit, the question unspoken but obvious on his face. She's perfect, Sergeant. I wouldn't know there'd been any work done if I hadn't seen the repair myself. mark her serviceable, and let's get her on the readiness board. The scramble order came through at 13:47 hours on October 20th. Vector, heading 095, Angels 15. Bandits approaching Dover Strait from the direction of Cap Grinet. Wellum was strapped into the repaired Spitfire within 90 seconds, Merlin already roaring as ground crew yanked the chocks away. 11 fighters from 92 Squadron clawed skyward through broken cloud, forming up in loose sections as they climbed eastward toward the incoming raid. Sector Control's clipped voice crackled through the headset. Scaffold leader, bandit stream estimated 40+ with escort at Angels 18. Range now 20 miles. The fabric repair would face its true test, not in carefully controlled maneuvers over friendly territory, but in the chaotic violence of air combat, where G-forces arrived without warning, and airframes endured stresses no test pilot would deliberately inflict. At 14,000 feet, Wellum spotted them. A loose formation of Heinkels 111 bombers in their distinctive greenhouse canopies stepped up between 16,000 and 19,000 feet, with a high cover of Messerschmitt Bf 109s weaving above them at 22,000 feet. The geometry of interception required climbing through the fighter screen to reach the bombers, accepting the temporary disadvantage of lower altitude, whilst depending on the Spitfire's superior turning performance to survive the bounce that would inevitably come. Squadron leader Jamie Rankin, leading the formation, made the tactical calculation instantly. Scaffold aircraft, ignore the snappers. Go for the bombers. In we go. 11 Spitfires pushed their throttles through the gate into emergency boost, Merlin engines screaming as manifold pressure climbed to 12 pounds per square inch. Power settings that shortened engine life dramatically, but extracted every available horsepower. Wellum's fighter accelerated through 320 miles per hour as they closed the range, the bombers growing from dots to identifiable aircraft with astonishing speed. The first pass happened too fast for conscious thought. Wellum selected a Heinkels on the formation's left edge, rolled inverted, pulled through into a diving quarter attack from the port beam. His thumb found the firing button on the control column's spade grip. 8 Browning machine guns erupted simultaneously, sending 160 rounds per second downrange in converging streams. Tracer rounds arced lazily before accelerating past his canopy. The Heinkels port engine, cowling, sparked as strikes registered. Then Wellum was past, pulling up and left to avoid collision, his Spitfire loaded to 5 Gs in the climbing turn. That maneuver, the abrupt transition from a 400-mile-per-hour dive to a 5G pull-up whilst firing, was precisely the kind of stress McCudden's repair needed to survive. The fabric section experienced rapidly changing aerodynamic loads, compression during the dive, then sudden tension as Wellum hauled back on the stick and the tail surfaces bit into the airstream. The doped linen flexed microscopically under load but held its shape, distributing stress across the entire repair area rather than concentrating it at any single failure point. The rib stitching absorbed the differential movement between fabric and metal structure, each stitch stretching slightly before recovering, functioning exactly as designed. A Bf 109 came down on Wellum's tail during his climb, cannon shells cracking past close enough to hear over the engine noise. He broke hard right, then reversed left, pulling the Spitfire through a series of violent direction changes that made his vision tunnel and his body feel impossibly heavy. The 109 couldn't match the turn rate and overshot, giving Wellum separation to dive away toward cloud cover. In those 15 seconds of defensive maneuvering, the fabric repair experienced load reversals that cycled from positive to negative G, compression to tension, dozens of times. The engineering that McCudden had calculated on faith, the principle that fabric's flexibility would absorb stress rather than concentrate it, was proving itself under fire. The squadron reformed at 12,000 feet, missing 2 aircraft, but with most pilots reporting strikes on the bomber formation. Sector Control vectored them toward a second raid, developing over Dungeness, and they climbed back into the fight. The repaired Spitfire performed flawlessly through 2 more engagements that afternoon, accumulating 1.8 hours of combat flying time that included multiple high-G maneuvers, 3 gun-firing passes, and 1 emergency dive to 450 miles per hour, indicated when a 109 got behind Wellum in a climbing fight. On October 21st, the same aircraft flew 2 sorties, a morning patrol that intercepted a Dornier reconnaissance machine over Ramsgate, and an afternoon scramble against Junkers Ju-88 bombers attacking coastal convoys. Wellum shared in the probable destruction of one Ju-88 that was seen streaming glycol and losing altitude toward France, though no confirmation was possible. The combat report noted 8 seconds of firing time at 300 yards range. Strikes observed on port engine and fuselage. Enemy aircraft last seen descending through cloud at 6,000 feet, 15 miles south of Dover. The 3rd mission on the fabric repair came on October 22nd, during an afternoon engagement with a mixed formation of Heinkels and Ju-88s approaching the Thames estuary. This sortie proved the most violent yet. 92 Squadron intercepted the bombers head-on, closing speeds exceeding 600 miles per hour combined, with barely 3 seconds of firing opportunity before breaking away to avoid collision. Wellum's combat report described the encounter with characteristic understatement. Fired 4-second burst at He-111 from dead ahead. Range 400 yards, closing to 150 yards. Observed strikes on nose, glazing and port wing route. Broke down and right at minimum separation. Heavy return fire from bomber defensive positions. Holes observed in port wing, trailing edge after landing. Those holes, 5mm rounds from the Heinkels dorsal gunner, had missed the fabric repair by 18 inches. The gunner had been aiming at the cockpit. His deflection was off slightly, and the rounds punched through the metal wing instead of the fabric-covered fuselage. Pure chance, but it underlined the reality every RAF pilot lived with. Life on a knife edge, and sometimes 18 inches decided it. Across those 3 missions, the repaired Spitfire logged 11.4 combat hours, time between 8,000 and 22,000 feet, speeds from stall to maximum, G-loads from -2 to +6, gunfire vibration, and return fire punching holes in non-critical structure. The fabric repair, which McCudden had guessed might last a week before replacement, showed no deterioration. No stitches had pulled, no dope had delaminated, no panels had split or ballooned. The field expedient had quietly become a permanent modification. The structural engineering principles that made McCudden's repair successful weren't immediately obvious, even to the technicians who'd executed the work. On the surface, bonding fabric to damaged metal seemed like putting a plaster on a broken bone. Cosmetically reassuring, but structurally weak. Yet the repair worked precisely because it challenged peacetime assumptions. The key lay in understanding how different materials take load, and how combining dissimilar materials can produce properties superior to either alone. Aluminum alloy, the Spitfire's primary material, offered a superb strength-to-weight ratio, good fatigue resistance, and formability. But once a crack starts, cyclic loads propagate it quickly. Stress at the crack tip exceeds yield, and each cycle grows the fracture until catastrophic failure. The cannon damage created exactly that. A crack in a primary member that would lengthen with every flight until the longeron failed. McCudden's riveted aluminum doublers addressed crack growth through load path redundancy. Rivets shifted load from the damaged longeron into the doubler, around the crack, and back into sound structure downstream. In modern terms, a doubler reinforcement converting a critical member from doomed to serviceable. The fabric contribution was more than aerodynamic tidying. Properly doped linen forms a stressed skin membrane, carrying load in tension. It's flexible relative to metal, yet strong in pull, and, crucially, spreads load across surface. Under 5G, every 10 pounds weighs 50. The tight fabric increases tension uniformly, letting all 192 stitches share load. If one starts to fail, neighbors pick up the slack, preventing cascade failure. Equally important was damping. Thin aluminum transmits vibration well, great for feel, bad for fatigue. Engines, gusts, and guns send stress waves through the airframe. Millions of cycles breed cracks. Fabric absorbs vibration via microscopic flecks in the doped fibers. Pre-war RAE Farnborough tests showed fabric-clad sections transmitting roughly 40% less vibration than metal panels. Together, metal and fabric formed a composite system. Metal took compression and bending. Fabric took tension and soaked vibration while preserving airflow. Alone, each would fall short. Together, they met the operational demand. There was a thermal bonus. Aluminum's high thermal conductivity made it expand and contract with temperature swings, cold at altitude, heat on the ground, adding fatigue. Fabric, a poor conductor, insulated and accommodated expansion by changing tension rather than dimension, stretching microscopically to follow metal without adding stress. AM 1925, the RAF's fabric manual, was built on empiricism, not finite element theory. Its authors couldn't speak in stress maps and damping coefficients, but they knew what worked. Stitch spacing, dope sequence, fabric tension, honed by generations who learned via successes and wreckage. McCudden succeeded by following doctrine meticulously while adapting it to an unusual case. He didn't ask fabric to carry compression, he used it for tension and load spreading. Not elegant by peacetime standards, but a sophisticated, practical grasp of materials that many formally trained engineers would struggle to express. By late October 1940, word of the success had spread through Fighter Command's maintenance network. Other squadrons tried similar repairs with mixed outcomes. The difference wasn't materials. Everyone had fabric and dope. It was craft. Poor stitching, weak dope penetration, wrong tension, or misaligned doublers produced repairs that looked fine on the ground and failed in the air. The engineering holds. Execution decides survival. The Spitfire McCudden's crew saved in October 1940 didn't survive the war. Records show Category 3 damage in a landing accident at Biggin Hill in March 1941. Undercarriage collapse on rain-soaked grass, fuselage bent beyond economical repair. Struck off charge, reduced to components, the fabric section likely cut away during salvage. But the methods that kept it flying through those critical months outlived the airframe, preserved in institutional memory, and later in the practices of Britain's best restoration specialists. The Battle of Britain Memorial Flight, established in 1957 to keep wartime aircraft flying, operates the world's oldest airworthy Spitfire, P7350, a Mark IIA that flew with 266 Squadron in the summer of 1940. Its 8+ decades have seen many repairs and restorations, yet the maintenance philosophy remains strikingly close to wartime practice. In 2018, when BBM engineers found corrosion in P7350's rear fuselage frames, they faced McCudden's choice: replace with modern methods or repair using period-correct techniques to preserve authenticity. They chose authenticity and rediscovered why fabric repairs worked so well. The BBMF's chief engineer, squadron leader Paul Blacker, documented the process in the flight's archives. His team fabricated aluminum doublers using hand riveting akin to McCudden's, then covered the area with Grade A Irish linen, sourced from one of the last mills still producing aviation fabric, to 1940s specifications, finishing with modern cellulose dope, differing mainly by omitting certain toxic solvents. The accompanying engineering analysis quantified wartime intuition. Finite element stress models showed fabric covering reduced peak stress concentrations by distributing loads wider. Vibration analysis demonstrated fabric-covered sections had significantly lower resonant frequencies than all metal panels, less prone to harmonic excitation from engine vibrations. These weren't accidents. They were engineered advantages refined by decades of practice. The Duxford Imperial War Museum team found similar insights restoring Spitfire AR-213, a Mark 5B recovered from a Northern Ireland peat bog where it crashed in 1942. Conservators discovered intact original fabric on control surfaces, dope preserved by anaerobic conditions. Microscopy revealed astonishing workmanship, rib stitching so regular it looked machine-made, dope penetration so complete that individual linen fibers were fully encapsulated, and 7 coats where 5 were specified, evidence of a meticulous craftsman exceeding minimums. Chemical analysis showed the cellulose film had polymerized over 8 decades into a stiffer, yet still flexible matrix. Properly applied dope doesn't merely dry, it undergoes long-term cross-linking polymerization. Residual solvents and moisture continue reacting with cellulose chains, adding bonds and improving properties up to a point. Modern regulations complicate historically accurate fabric repairs. The Civil Aviation Authority requires engineering data absent in 1940, stress calculations, material specs, inspection intervals, test results. BBMF engineers have reverse-engineered what wartime crews did by feel, producing models and data to prove what McCudden knew. Fabric on metal repairs work when executed correctly. That bureaucratic need brought a benefit, a comprehensive understanding of why field repairs succeeded. Modern analysis confirms fabric over metal creates a mechanically advantaged hybrid, metal for compression and stability, fabric for tension and damping. Together, performance beyond either alone. The techniques now aid restorations where parts don't exist. A 1930s de Havilland Dragon in New Zealand received fabric over repaired aluminum frames straight from Spitfire practice. An American Hawker Hurricane restoration found fabric over repaired frames not only authentic, but superior to new metal skins, which would demand costly tooling and introduce hard stress steps at thickness changes. Remarkably, Airbus engineers developing lightning strike protection for composites studied historical fabric techniques. Modern carbon fiber can suffer hidden damage. Thin metallic fabric bonded to composite skins spreads strike energy widely. Load distribution in a new domain, echoing McCudden's principle. An 85-year-old battlefix feeding 21st century aerospace. When P7350 flies a display, few realize they're seeing principles proven under fire over Kent in October 1940. The Spitfire's lines and elliptical wings draw the eye, but somewhere within are repairs born of a sergeant fitter who knew survival sometimes demands improvisation, and that improvisation, done with craft and insight, can outperform perfection. McCudden's fabric and adhesive repair wasn't a desperate expedient. It was sophisticated engineering in the guise of simplicity, and it kept a pilot alive when Britain needed every fighter and every pilot it could muster. That the same principles still keep historic Spitfires airborne 8 decades later testifies not to the materials alone, but to understanding. How materials behave under stress, how loads distribute through structures, and how the old ways endure because generations refined them through hard-won experience.